Great. So thank you, everyone. I'm really happy to be able to speak here today. And I'm going to talk here about some work that I've done at Columbia over the past couple of years. And this is all in collaboration with the LEAP Center at Columbia. So LEAP is the Learning the Earth with Artificial Intelligence and Physics Center. And this is an NSF Science and Technology Center that's focused on using methods from machine learning and data science to try to improve climate model parameterizations. And so I just wanted to acknowledge first, like many different co-authors who have contributed to the work that I'm going to show here today. And I'll start with some motivation for this work, which is a better understanding of how clouds and convection play a role in the Earth's climate. So if we think about a typical climate model, the climate model grid box is going to be something on the order of like 100 kilometers. And that means in the atmospheric portion of the model, we have to parameterize all of these processes shown on the right that are at the subgrid scale in the model. So these are things like shallow and deep convection, the radiative effects of clouds, as well as cloud microphysics. And we know this remains a major source of our climate uncertainty. So this figure comes from Zelinka et al. 2017 from this Nature Climate Change paper, and it's basically showing the global average surface temperature anomaly from the year 1850 projected up until the year 2100 across the ensemble of models in CMIP5. And so we see this fairly significant model spread, something like the order of about 2 to 5.5 degrees Celsius across the ensemble of models. And this model spread is very strongly linked to the net cloud feedback in the models. So basically the response of the clouds to warming. So we think if we're able to improve our ability to represent these subgrid scale processes, then we'll be able to, kind of reduce this amount of spread and improve our ability to project future climate. So that's really the big picture motivation for this work. But we, of course, know that cloud processes are something which are really challenging to model across these different scales because they're complex, nonlinear, and inherently multi-scale. And here I'll talk a lot about cloud microphysics. So this is this nice figure from Hugh Morrison's paper, recent review paper, that's showing basically all of these cloud microphysical processes. So this is like the interaction, all these processes that govern the interaction and growth of individual droplets and ice crystals inside of a cloud. So if we wanted to model all of the physics of these processes, we would need something like a direct numerical simulation to explicitly model how the cloud evolves at the smallest scale. But we can't possibly do this on the order of the climate. So even when we go to something like a large eddy simulation, where we can model like a single cloud or a cloud field, we already have to have some way to parameterize these microphysical processes. And then when we get to like the scale of climate, we're really having to come up with some very simplified representations of the microphysics. And we even have to parameterize the larger scale cloud processes. So we have this sort of parameterization squared problem. So there's still a lot of things that we really don't know about how to represent these processes, and especially across all these different scales. And we still don't know all of the physics at the smallest scales in these clouds, especially across all of the regimes in the atmosphere that we're going to be interested in, and especially that we might need to represent in the case of like a changing climate. We also don't really have an optimal representation of these cloud processes in current models. And we're not really sure exactly how to do this. And then finally, we don't necessarily know how to consistently represent these processes at different scales across all of the different, at the climate scale, particularly like how to represent all of this complexity, but at the right level that we need. So scientific machine learning is something that has really kind of revolutionized the field in the last couple of years and is helping to solve some of these challenges. So this is kind of if this is sort of our current day picture of what clouds look like in our model, then some of these methods can hopefully help us move closer to these this much more accurate representation of these cloud processes. So things that have been helpful are things like emulation of very computationally expensive models, as well as hybrid physics machine learning models where we know some of the physics, but also might have some unknown physics. And then methods like neural ordinary differential equations or neural operators can be used to directly be integrated with solving partial differential equations. There's also been work on things like reduced order modeling, as well as equation discovery. And I might also add here something like these perturbed parameter ensembles that have been a big point of discussion recently. So This is kind of an optimal time also to do this because there's so much data now available from both remote sensing observations as well as in situ field campaigns that we're not even really taking advantage of all of this. There's also been work on improving these high resolution cloud resolving models, as well as improving large eddy simulations and the ability to accurately model cloud processes. And then, of course, there's been this huge explosion in the application of machine learning to the physical sciences, like not just in the atmospheric and climate sciences, but also in physics and biology. And so this is really accelerating the development of these types of algorithms and the identification of specific problems that they can be applied to. So like all of these together means that we can really improve our system understanding using these types of methods. So here I'm going to talk about a couple of studies focused on each of these different problems that we've done over the past couple of years. And I'll focus first on this problem on looking at some of the specific microphysical process rates and how we can potentially improve our understanding of these using relatively limited observational data sets. So here I'm going to focus on the vapor deposition process, or what's called depositional ice growth. And this is basically, once we have an ice crystal that forms in the atmosphere, how the ice crystal will grow through the direct deposition of water molecules onto the surface of this ice crystal. And so we can go to like Prue-Precker and Klutz, which Klutz is Cloud Microphysics textbook, and we can write down this ordinary differential equation, which tells us the rate of change of the mass of this ice crystal as a function of the saturation, temperature, and something about the shape of the ice crystal, as well as how quickly water molecules diffuse to the surface of this ice crystal. So this is basically the capacitance model for ice growth with some corrections for surface kinetic effects. And so we have a fairly good understanding of this model, although there's been a lot of disagreement, particularly about this parameter, which is known as the deposition coefficient. And it basically tells us how efficiently water molecules will attach to the surface of this growing ice crystal. And this like parameter has typically been assumed to be a constant value or simply ignored, although there's some recent work that has demonstrated that it's likely a saturation and temperature dependent function. And this parameter not only tells us how efficiently ice grows, but it can also be used to parameterize the shape of pristine ice because we can have different deposition coefficients on different surfaces of the ice crystal surface. So that's really the motivation for this, is trying to better understand this equation and whether we can learn some of that unknown physics in this equation. So the observational data sets that we have come from laboratory experiments, because we really need these detailed experiments to try to put constraints on these types of processes. And so these are single ice crystals that are grown at constant temperature and supersaturation. And this data set comes from Jerry Harrington's group. And so I have 307 experiments of individual ice crystals that are grown in the chamber. And I'm just showing here the saturation and temperature range of all of these different experiments, and also whether they were homogeneously or heterogeneously nucleated. And so what the data sets look like is these time series of the mass of the ice crystal relative to its initial mass as a function of time. And so since we think we have a pretty good understanding of this model and we don't have a lot of data, I'm going to start with this ordinary differential equation and then just only try to learn the functional dependence of that deposition coefficient parameter by replacing that with a neural network. And so that neural network is going to be effectively a function that is taking in the saturation and temperature, and then given the weights of the neural network, it's going to predict a value for alpha. And we also want to know the observations that we have are related to the mass of the ice crystal, but we're trying to put constraints on this parameter, which is in the mass growth rate equation. So I also need to be able to integrate over this equation. And so I can borrow this idea from this Chen et al. 2018 study of these neural ordinary differential equations. And this is basically this idea that you can integrate directly over some unknown function, just like using typical numerical ODE solvers, and perform efficient backpropagation, sort of while simultaneously optimizing this unknown function while integrating over it to learn the correct weights for that neural network. So I'm going to use this idea to create this node model, which includes all of this physics plus this unknown parameterization for the alpha function. And in order to learn what the alpha function is, I'm going to optimize the node model directly against the observational data sets. And I'm going to do that across all 307 experiments simultaneously. And so basically what I'm trying to do is minimize the distance between the model and the observations by learning the optimal functional form for alpha that's going to minimize that distance. And so I first will show you this on a set of synthetic data where I have a known functional form for alpha, which comes from the Nelson and Baker parameterization for the deposition coefficient in terms of saturation and temperature. So here I'm just showing a subset of these time series after I've optimized the node model against the observations using stochastic gradient descent. And so you can not really see much difference here between the model and the observed time series. And I can then, once the model is optimized against the observations, all the information is then contained in that neural network, the trained neural network, which is replacing the alpha function. So then I can look basically at what that trained neural network is telling us by like giving it the values for saturation and temperature and then looking at its predictions for alpha. And I'm going to compare that here with the Nelson and Baker parameterization, which I put into my synthetic data set. So if I look at what the neural network learned for alpha versus the parameterization that was put into for the synthetic data, it's like doing an extremely good job of actually being able to reproduce that function. And this, I should say this is actually a pretty complex function. It's like a hyperbolic tangent function. So it's able to do a very good job of like recovering like the true value for alpha. So since this works fairly well on the synthetic data set, I'm then going to apply this to the real data set of these 307 ice crystals. And so this is basically what I get when I minimize the distance between the model and the observations for this particular model for depositional ice growth. So you can see that overall, there's like much more significant, even though I've optimized the model here, there's more significant deviations between the model and the observations, which suggests that even though I've tried to optimize alpha across all these experiments, this particular functional form for alpha may, kind of be structurally deficient in the sense that we can't do a perfect job of actually reconstructing what we expect to see in terms of the time series. And I can also then, similar to what I did before, look at what it learned for alpha. But as I said, this particular model doesn't seem to really give us the optimal fit. So it's quite a bit different than the Nelson and Baker parameterization. And overall, I don't particularly trust this alpha because it's not giving me a really optimal ability, or it's not doing a great job of reconstructing all the time series. So we next decided to consider a less constrained model, but using the same type of approach. So this model is using, so basically I'm rather than having the, so much structure in my initial model that I'm trying to learn, I'm going to instead try to learn effectively the entire denominator in this capacitance ice growth model. And I'm going to learn this relative to what we would expect for a spherical ice crystal in the diffusion limit, which is this GC parameter. So I'm just learning this sort of ratio between what we actually observe for our ice crystals and the diffusive limit for a spherical ice crystal. So this function now takes in the mass of the ice crystal as well as the temperature and supersaturation. But I can do the same thing where I'm then going to try to minimize the distance between the model and the observations for this functional form. And so here I'm showing again a subset of the results. And overall, it does a significantly better job of being able to reproduce the majority of the time series, although you can still see that there are some deviations here for some of the experiments. So potentially there's still a better form for this that we could come up with. But at least in terms of learning this functional dependence, I can then look at what it actually learned in terms of this G over GC ratio, which is what I'm showing here in terms of the temperature, the mass, and the supersaturation. And then the color here is that learned G over GC ratio from the model. And so we can see that it's sort of a smoothly varying function overall in this space. And so the last thing that I've been looking at is whether we can actually come up with a functional form that can describe what the neural network learned so that we can like go back to our ice growth model and have a a symbolic expression that we can directly interpret. So to do that, I'm using symbolic regression. This is using the Peiser library, and this is basically using a genetic algorithm to try to come up with an optimal functional form that is going to be describing this functional dependence. And so I get out this learned functional form, and this is in terms of non-dimensionalized mass, temperature, and supersaturation. And I can also then compare the symbolic regression equation with what the trained neural network was predicting. So this is some work that we have recently have accepted in the NeurOps ML for Physics workshop. There's still some things to work out, like how to include uncertainty in this type of framework, but that's sort of a work in progress. And one other thing that we've been looking at is also applying this type of method to the AIDA chamber to see if we can get constraints on alpha in that case. But that is a little more complicated because we don't directly observe the mass of a single ice crystal, but rather the aggregated mass of multiple ice crystals in terms of like the ice water content in a volume of air. So in that case, we actually need a bin microphysical parcel, a differentiable bin microphysics model to do that type of prediction. So in any case, these types of methods are useful for trying to learn unknown physics in these cases where we have like a relatively limited and sparse data set. So I think there's a lot of promises for using these types of methods for other microphysical problems as well. And I'll next talk about a study on thinking about how we can improve the representation of cloud microphysics in models at different scales. And so for this, I'm going to not talk about ice, but I'm going to talk about warm rain microphysics. This was a recent study that we did that was focused on looking at the collision coalescence process. And so if in a warm rain cloud where we only have liquid droplets, the microphysical state of the cloud can be effectively described by its droplet size distribution, which is going to be the spectrum of droplets of various sizes in a cloud. And so if we think of how we typically model a cloud, we would add a grid to this domain, and then within a single model grid box, we have to have some way to represent the droplet size distribution. And there's a couple of approaches that people typically use for this. There are these bulk parameterizations where we basically just track the statistical moments of the droplet size distribution. And the statistical moments are going to be related to observable quantities such as the number concentration of drops in this model grid box, as well as the mass mixing ratio of drops in the model grid box. And then sometimes people also use the radar reflectivity. And in that case, when we have microphysical processes applied to these moments, we generally assume some analytical functional form for the true droplet size distribution and then determine how the moments would change assuming that assumed analytical functional form. A more accurate approach that people use is to, instead of tracking just the moments of the distribution, they discretize the distribution into bins of various sizes and then look at the like how this bin droplet size distribution evolves as though we have the physics acting on particles of that specific size that bin represents. So overall, because the bin distributions have many more degrees of freedom, we think that they're generally more accurate, but they're also much more computationally expensive. So for a typical bulk parameterization bulk scheme, you're tracking something like 4 to 6 parameters in each model grid box to describe the droplet size distribution. And in the bin schemes, you generally have to keep track of something like 30 to 70 parameters in each model grid box to track the droplet size distributions. And in the last couple of years, there's also been a lot of work on these Lagrangian particle-based approaches. So these are sort of conceptually different than the bulk or the bin in that we're no longer tied to the model grid box. We actually advect some representative superparticles around with the flow fields, but these are like extremely computationally expensive. So we would need something like hundreds of these super droplets within each relative to each model grid box to be able to accurately represent or predict the evolution of the cloud. So these are really limited to these smaller scale process level studies. So for something like a climate model, we're still going to be really limited to these much more simplified bulk approaches, or something like these simplified bulk approaches. And although for these data-driven methods like the bin microphysics approaches and the Lagrangian superparticle schemes can really provide higher fidelity ground truth data sets for training our machine learning models. So once we have chosen in our bulk model a representation in terms of moments, we also, as I said, need to think about how the process rates will affect that particular representation that we're actually tracking in our model. So for this study, we focused on the collision coalescence process, and that's basically when we have smaller droplets that collide to form larger droplets, and then larger droplets that fall through the cloud and collect smaller droplets. And so in a typical bulk microphysical scheme, one additional assumption that we make is that we actually have two separate populations of liquid droplets. We have these cloud droplets that don't precipitate, and then we have the larger rain droplets that do precipitate. And so in that type of two category approach, we actually have three separate process rates that we have to keep track of for autoconversion, accretion, and self-collection. And so autoconversion is basically, it's not really a physical process, it's just when the cloud droplets have collided enough that they've become a rain droplet. And then accretion is when we have sort of the larger droplets falling through the cloud and collecting the smaller droplets. And then we also sometimes track self-collection, which is going to change the number concentration, but not the mass mixing ratio in each category. So these are generally expressed in most bulk parameterizations in terms of power laws of the cloud and rain moment so that we can have closure. And so I'm just giving here this example from Krudenov and Kogan of the parameterization for the mass mixing ratio of rain for the autoconversion and accretion processes in terms of power laws of the other moments in the scheme. And so how those power laws are determined is generally something, so like in Krudenov and Kogan, they took an LES simulation with a bin microphysics scheme to explicitly determine these autoconversion and accretion rates. And then they looked at coming up with bulk autoconversion rates that were sort of like optimally fitting the explicit autoconversion rates in order to determine the, the correct power law relationships here. So there are some limitations with this type of approach. We have these a priori representations of the droplet size distribution in terms of cloud and rain moments that we don't necessarily know are the optimal representation. And we also make some assumptions about what types of functional forms we're looking at for the microphysical process rates. So this leads to both structural and parametric uncertainty, and we know specifically for collision coalescence that the artificial threshold between cloud and rain is something which is problematic because we can't fix the same threshold across all regimes in the atmosphere. So like a drizzling cloud would need a different threshold than a heavily precipitating cloud. So the approach that we decided to explore instead is to use reduced order modeling to learn a latent bulk representation scheme directly from the higher fidelity bin or superdroplet microphysics schemes in this case. And so reduced order modeling is something, it's an idea that comes from, it's been developed a lot in the fluid dynamics community, and it's basically like a reduced order model is a model that is going to have many fewer variables than your full complexity model, but it's going to be able to reproduce the majority of the behavior of your full complexity model. And so the particular approach that I'm looking at is based on this architecture, which is known as an autoencoder. And so basically, I'll show sort of the schematic of what I'm doing here. I'm going to take as input the droplet size distribution. I have this neural network, which is known as the encoder function. It's going to learn a lower dimensional representation of this droplet size distribution. And then I'm within this lower dimensional or latent space representation, I'm also going to learn this collision coalescence process, how it would act on that particular representation of the droplet size distribution. And then I have another neural network, which is known as the decoder function, that's going to then reconstruct the droplet size distribution after the collision coalescence process. And so this type of architecture can be trained by looking at by reducing the reconstruction loss between the predicted droplet size distribution at the next time step and the true droplet size distribution at the next time step. So basically, this is going to give me both this reduced order or latent representation of the droplet size distribution, and I'm also going to learn in this lower dimensional representation some type of latent dynamics on this latent representation, which is going to be these microphysical processes. So to test out this method, I'm looking at a relatively simple kinematic driver model, but it's going to drive the tau bin microphysics scheme. So this one-dimensional kinematic driver model just simulates the column of air under the action of a sinusoidal updraft. And we have 16 different cases with different initial conditions for aerosol concentrations and updraft speeds to give us a range of conditions for training the models. So actually, first I need to ask, like, how many variables, though, do I need in that lower dimensional representation? Because that's effectively just a hyperparameter of the model, this autoencoder type architecture. So to do this, I looked at this idea that was developed by Chen et al. In this Nature Computational Science paper that was recently published, where they were looking at some dynamical systems and basically videos of dynamical systems, and then trying to learn from the videos, like how many degrees of freedom you would need in a model for that dynamical system to predict the future state of the physical system. And what they found was that they could use something which is called the intrinsic dimension of the system. And this is basically the topological dimension of the lower dimensional manifold on which the dynamics is assumed to evolve. And this is a good approximation for the number of independent degrees of freedom that you need in your model. And so there's a number of different algorithms to estimate the intrinsic dimension. So I just looked at a couple of different ones here, but I basically applied their same method to my droplet size distributions. And I find that the intrinsic dimension for collision coalescence, at least for the spin microphysical model, is something like 3. So that suggests that we need at least 3 variables in our lower dimensional representation to predict the collision coalescence process. So then I can look at how I can learn both the representation of the droplet size distribution, as well as a operator, which is describing this collision coalescence process in this lower dimensional representation. And here I've already I'm assuming that that lower dimensional representation now has a site, like it has 3 variables based on the intrinsic dimension of the system. So this is a slightly different architecture than what I showed before. So rather than directly trying to predict the future state of the system, I'm going to try to separately learn the collision coalescence process as an operator in the latent space representation. So basically, to do this, I'm taking the droplet size distribution, the current time step, I'm learning a lower dimensional representation of that, and then I'm learning to reconstruct the droplet size distribution at the same time step. And then I'm going to take this latent space representation, which is describing the droplet size distribution. I'm going to apply within the latent space representation, basically a linear operator. And that's because I'm assuming the action of collision coalescence is going to be a small linear change within the latent space representation. So then I'm going to take this latent space representation with this linear operator applied, and that's basically giving me the latent space representation at the next time step after the process of collision coalescence. So in order to reconstruct the true droplet size distribution at the next time step, I'm going to feed that back into this trained decoder function. And it's the same sharing the same weights as this decoder function here. So basically the idea is that the latent variables represent the shape and magnitude of the droplet size distribution, and then the action of the collision coalescence process in that latent space representation is basically encoded into this this matrix. And this is basically the same idea as using a variational autoencoder to learn the Koopman operator for a dynamical system. So we train this by minimizing the reconstruction loss for the droplet size distribution at the current time step, as well as the next time step, as well as the difference between the latent space representations at the next time step. And so I'm going to show now what these latent variables look like in space and time, but I'll first show what the typical bulk variables look like in space and time for just one of the cases in our one-dimensional kinematic driver model. So this is basically showing the height in the atmosphere at these 20 vertical levels, and then as a function of time, like how the cloud and rain moments evolve. And I'm showing on the top the cloud mass mixing ratio, and the bottom the rain mass mixing ratio. And what we see is there's initially we have a lot of smaller droplets, and then over time through the collision coalescence process, they basically evolve into rain droplets and they rain out of the cloud. And this happens 3 times because we have this sinusoidal updraft. And I'm showing at that 6-kilometer level also the true droplet size distribution from the bin scheme. So I can now show you what these 3 latent variables look like. So they're kind of like continuously varying in space. We don't see that sort of clear separation between cloud and rain moments. And you really need all 3 of these variables together to interpret what that means in terms of the droplet size distribution. And so we can also then look at, use the train decoder function to map out what these latent variables mean in terms of this droplet size distribution. So this is what I'm showing here. It's sort of what we call a latent manifold. And then I'm just showing representative droplet size distributions, and I'm showing for visualization purposes this along the two directions of greatest variance in the data. So if you look carefully, what we basically learn is something about the unimodality or the bimodality of the droplet size distributions, as well as like where it's placing the relative like cloud and rain modes in the droplet size distribution. So these are the types of variability that we would expect for collision coalescence. The last thing that we looked at in this study was thinking about like when we have these bulk representations where we've effectively compressed the information from the higher fidelity true droplet size state of the cloud in terms of its droplet size distribution, like where are we actually losing microphysical information in the cloud? So to do that, I'm going to basically look at the reconstruction loss, that's just defined as the difference between the reconstructed droplet size distribution and the true droplet size distribution. So I can directly do that for the latent variables because I have that trained decoder model, but for the typical moment-based representations, I want to compare. So I'm going to train another model, which is going to learn to reconstruct the droplet size distributions from the cloud and rain moments. So it basically has a very similar architecture to the decoder that was used for my latent variable reconstruction. And so what I'm showing here is the reconstruction loss from the moments for that case that I previously showed on the left, and then the reconstruction loss from the latent variables in space and time for the latent variables. And so like more red means worse reconstruction. And so we can see with the moments we're doing a worse job reconstructing the true microphysical state of the cloud in terms of its droplet size distribution at these early stages of rain formation. And this is something that I think is consistent with what we already knew about some of the limitations of these like 2-moment bulk representations for collision coalescence. But we do see that the latent variables do a better job of accurately reconstructing these early stages of rain formation. And then looking across all of the droplet size distributions in our independent test data set, and also averaging metrics for 10 random initializations, we find that overall the latent variables do about 2.5 times better at reconstructing the droplet size distributions than the typical bulk variables in terms of moments. And so this suggests that like we don't actually necessarily need more complexity in our bulk schemes, although there are still some challenges to think about how we might use this type of these latent variable representations in an actual climate model. So this is still some work that we're thinking through, is like how these types of representations might actually be interfaced into a model. But at least this initial study just exploring this approach was like published this last year in James. And I will talk really briefly about this. This was some work that was done with Stefan Mont's group at UC Irvine, and this was work led by Eustace Will, who was a PhD student in that group. And he was looking at some data sets from a large eddy simulation of a stratocumulus case that had a bin microphysics scheme. And he looked at taking the droplet size distribution at each space and time point and encoding that into a latent variable representation. So again, he uses 3 latent variables here, and then he projects that onto here in terms of the visualization. These 3 variables are projected onto RGB. So this one color is basically indicating the value of these 3 latent variables. And so I'll just play, or actually, so the colors here, in this inset plot, it's showing like what the colors mean in terms of the reconstructed droplet size distribution. So like more yellows and pinks are these smaller droplet size distributions, and like more blues are these larger droplet size distributions. So show how the simulation evolves. So we first initialize the simulation. We have a lot of pinks and yellows, and then as rain bands develop, we see more of these blue and greens as the droplet size distributions evolve to these larger sizes. So one other way that we can think about this is actually thinking about visualizing how this whole cloud field evolves in this microphysical, in this latent variable space. So this is basically showing the same simulation, but it's in terms of this like first latent variable, this second latent variable, and this third latent variable. And then we're just showing here the three, or all of the droplet size distributions in space in that latent variable representation. So you can see initially we have sort of all of these droplet size distributions here, and then over time, like as the cloud field evolves to these rain, we see it sort of follows this path in this latent space representation. So one thing that we looked at in this study was also seeing like how different levels of CCN concentration impacted this latent space representation. And it actually follows basically the same path in the latent space representation. It just, the aerosol indirect effect just basically impacts like how quickly it moves along from like one location in the latent space representation to another. So this particular study that it was like published in the NeurIPS ML for Physics workshop last year, but it's sort of just, we're just looking at this sort of as a visualization technique, but you could also imagine that these types of approaches might be useful for thinking about like kind of describing the microphysical state of the cloud, of this entire cloud field at the subgrid scale in a very compact and simplified way that's telling us something about like where the, sort of microphysical state of the cloud is at any particular time. I think for the sake of time, I'm going to skip this, but this is some work that we did this past summer, led by Oben Sturm, where we were looking at basically trying to look at the thermodynamic histories of individual superdroplets in an LES cirrus simulation, and just like seeing if we can find sort of characteristic trajectories. But he'll be talking about this more at the AMS conference coming up. So I'll just skip now to this last study that I wanted to talk about, where we were looking not at cloud microphysics now, but rather these larger scale, how we might parameterize these larger scale convective processes at different scales. So coming back to this figure that I showed at the beginning of my talk, so in a climate model, we do have to like parameterize deep convection, so these like larger scale storm systems. And all deep convective schemes really make this assumption of what we call the quasi-equilibrium hypothesis, which assumes that there's this separation of scales between what is happening at the grid scale in the climate model, so like the prognostic variables that we track, and then what's happening at the subgrid scale, so sort of like unresolved physics that we're not keeping track of. So all deep convective schemes basically make this assumption, but it's not really like implicitly tested. And we know that in general, most climate models do rain too little and also too often. And this could be due to the fact that there is this unresolved physics that we're not fully accounting for at the subgrid scale. So one approach that people have discussed for deep convective schemes is to have what we call a stochastic parameterization. So we can basically represent this unresolved physics in some stochastic way. But we know that convection is not something which is really truly stochastic. It's actually something that organizes at different scales, and it also generally becomes more organized over time. So there was some work by Mapes and Neal in 2011 where they suggested that one way to improve climate model deep convective schemes is to include a parameter for what we call cloud spatial organization at the subgrid scale. So this is as an alternative to trying to parameterize entrainment in mass flux schemes. So we decided to see if we could explore this using a data-driven approach. And so the data sets that we're using here come from the Diamond simulation, which was this model intercomparison project for global storm resolving models. And a global storm resolving model is something, basically a climate model that is run at very high resolutions, where we no longer have to parameterize deep convection because we can sort of resolve deep convection. So like the climate model, the grid boxes in these models are something like 2 to 4 kilometers rather than 100 kilometers. So the trade-off here is that we can't simulate the atmosphere for very long because these simulations are so expensive. So they're really only able to simulate sort of transient climate response, which is still really useful for evaluating things like deep convection. So for the Diamond simulations, they focused on simulating 40 days and nights. And these are also atmospheric experiments only. And the data set we focused on was this global SAM model. So this is just some of these Diamond models, and this is the actual Earth from the Himawari viewpoint. So going back to our question about how we might parameterize cloud organization at the subgrid scale, So I guess I should just say by organization, I mean that we initially have sort of random convection, and then over time it becomes more clustered and more organized within the domain. And there's actually many different metrics that have been proposed for cloud spatial organization. And they were nicely compiled in this Jansen et al. GRL paper in a Python library. So we took this library and applied it to 100 kilometer by 100 kilometer patches of the precipitable water fields from the global SAM model. And this is focusing on the tropics over the oceans to just look at how correlated these different cloud spatial organization metrics are. And there's actually like a lot of not a lot of correlation between all of these different metrics. So they're all sort of telling us different aspects of how you might describe organization at the subgrid scale. We don't really know which cloud organization metric might be the most informative for helping to look at things like improving precipitation at the climate scale. So we instead decided to look at whether we could effectively learn this some type of organization parameter directly from the subgrid scale. And so we're going to compare here two different models. So the top model is just kind of looking at this quasi-equilibrium hypothesis. It's basically taking in these high resolution fields, coarse graining them down to what would be observed only at this climate scale, so these large scale variables, and then it's just taking a neural network, it's trying to map these large scale variables to the prediction of precipitation at the next time step. So this is sort of our baseline neural network model. So this basically allows us to ask, is precipitation at the climate grid scale predictable from large scale variables only? And we're also going to compare this. Oh, I should say the large scale variables here are the humidity at 2 meters, the temperature, the sea surface temperature, and then also the precipitable water field, which is the column integrated humidity. And then the model that we're comparing this to is this organization-informed neural network. It basically couples an autoencoder with a neural network. So we're going to take the high-resolution precipitable water fields. We're going to learn some lower dimensional representation of that. And then we're going to take this lower dimensional representation, these org parameters, and concatenate that with our large-scale variables, and then use that to predict precipitation at the next time step. And then this model is actually trained end to end. So it's going to learn both of these simultaneously. And this basically allows us to ask, do we also need to include some additional information from the subgrid scale to improve our prediction of the precipitation at the next time step? And if so, what is the information that we need from the subgrid scale to improve this prediction of precipitation? So I'll show here the results for the PDF of precipitation. So since we're thinking at the climate scale, we're interested really in the probability distribution functions of precipitation. So this is basically the precipitation rate and the true value from the GSAM model is shown in blue, and then the predictions from that baseline neural network are shown in orange. And then I'm showing the same thing for the organization-informed neural network. So if you compare these two, you can see that for the baseline neural network, we're actually really missing the extremes of precipitation, whereas with the organization-informed neural network, we're actually able to do a much better job of actually getting the extremes of precipitation correct with this, when we just include a little bit of information from the subgrid scale about how organized precipitation is. And we can also look spatially at how correlated the predictions of precipitation are as well. So this is just showing the R-squared value for the baseline neural network. If it's more red, it's more highly correlated versus the organization-informed neural network at the bottom. So we also spatially do a much better job of having like a much improved prediction of precipitation across the tropics. And the last thing that we can look at is actually trying to interpret what was learned in this organization parameter. So to do that, we're going to use the, we also train this decoder function. It like maps from the organization parameter back to the high resolution precipitable water fields. So we can actually look at how, like using this, what these organization parameters mean in terms of the high resolution precipitable water fields. And for this, we again do this trick of looking at these two directions of greatest variance in the data set. And I should say here, the first direction of greatest variance actually explains something like 96% of the variance in the data. So the majority of the variance is explained along this direction. So here, this is basically mapping out characteristic high resolution precipitable water fields. And along this direction, we see that it's basically more organized convection, or sort of like less organized on this end and like more organized over here. And so this suggests that what these org parameters actually mean in terms of the high resolution precipitable water field is related to sort of how organized convection is at the subgrid scale. And in addition to that, we also found that these org parameters can be predicted autoregressively from their own history. So this also is indicative of that these parameters are telling us something about like how organized convection is over time. So overall, because we're able to significantly improve this prediction of precipitation, this suggests that using like a purely stochastic parameterization for deep convection is likely unnecessary. We could probably do much better by including some information about the organization at the subgrid scale instead. So I've talked about a lot of things, but I'll just quickly summarize. We've been looking at methods like physics-informed machine learning to improve constraints on microphysical processes that are observationally challenging to constrain, which can help us reduce some structural uncertainty in our cloud microphysical models. We've also been exploring approaches like reduced order modeling to develop simplified bulk microphysical models. And these approaches also seem quite promising for looking at things like how we can connect the microscopic evolution of clouds to their macroscopic evolution. And then finally, I talked about some work on looking at how we can improve our ability to predict precipitation at the climate scale by improving deep convective parameterizations. And so, yeah, with that, I just wanted to say thanks. I'd be happy to take any questions. And these are these are the papers that I talked about if anybody is interested in checking them out. So.
Okay, well, thank you very much for that very interesting and I would say information-packed presentation that you gave us today. And we have plenty of time for questions, so feel free to either raise your hand, put a question in chat, or also feel free just to unmute yourself and say your question.
Yeah. Yeah, and I should say also, you can also send me an email too if you think of something offline.
Okay, well, while everybody else is thinking of their